This lesson is on gas stoichiometry, which is a very important part of this unit, so you might want to pause videos, work problems, see if you can work the problem before I do and see where your understanding is, or rewind, and if you are having trouble understanding something, make sure you understand the gas stoichiometry part of it. So we're going to start with showing you how we actually get the molar volume of a gas, and we're going to use the ideal gas law to solve for the volume of 1 mole of gas at STP. And just so that we make sure that everybody remembers that STP stands for standard temperature and pressure, and that means that temperature is either 0 degrees Celsius, but because we're dealing with gas laws, we're going to say 273 Kelvin because all of our temperatures must be in Kelvin. And then the standard pressure is 1 atmosphere. So if we take those conditions, and it's telling us 1 mole of gas, so we're going to solve for volume. So it's going to be V is equal to nRT over P, and then we plug in those parameters. We get 1 mole times 0.08206 liters atmosphere over mole K, and then 273 Kelvin for standard temperature, and then 1 atmosphere for standard pressure. And when we put that in the calculator, you guessed it, comes out to 22.4 liters per mole of gas. And of course that is for any gas, doesn't matter what it is, at STP, at standard temperature and pressure. So if we're doing a stoichiometry problem, not even a stoichiometry problem, we're reading through a problem, maybe it's even on the AP exam itself, and we see, okay, I see nitrogen gas, this is going to be a gas law problem, but then I see those little magic 3 letters that I love to see, and that is STP. That means do a little happy dance, because this is a super easy problem, because we can use the 22.4 liters. Remember, we can only use 22.4 liters per mole if we are at STP. If we are not at STP, then we're going to have to do a gas law, PIV-NERT, and plug in the parameters that they give us in the problem. So then that comes out to, I need 3 significant figures, 7.0781 moles of nitrogen. Okay, so those are the quick and easy ones. Go grab those points whenever you see them on a test. The next one, also at STP, so I'm going to let you do that one. And then we are going to work problem 15, because problem 15 is a long, extensive problem. I'm going to warn you to write small when we're doing this. And I didn't include the question in my PowerPoint because I need all of the space to work my problem. So we're going to look at this problem. You have it in your notes. You have methane being mixed with oxygen when we ignite it. In other words, this is a combustion. We're going to form CO2 and water, and it wants to know the volume of CO2 formed. The problem is all 3 of these, both of the reactants and the products, are all at different pressure and temperatures. So we are going to have to actually work 3 different ideal gas law equations. So first thing is to balance the equation. So methane, when it is burned, is going to be plus 2O2, yields CO2 and 2H2O. So that is our balanced equation that we're going to be using. And so they give us information both about methane and both about oxygen. So it's a limiting reactant problem. And this is probably the first time you've seen a limiting reactant problem with gases. So we are going to work and determine which is limiting. So first step is determine limiting. So we're going to do that by solving for moles of methane, and then use the mole ratio to see how many moles of gas, of the CO2 gas that we can make. So, and then we'll do the same thing for oxygen and see which one is our limiting. So N is equal to PV over RT. So we're going to plug that in, 0.189. I'm sorry, just gave you the answer. 1.65 atmosphere from the problem. anytime we're working this problem, if you're wondering where I got that number, check the problem first. That's probably where it came from. At 2.8 liters divided by 0.08206. I know it has the units there, liter, atmosphere, mole K. And then 298 is what that particular substance was at. And I get 0.189 moles of methane. And then I go look at my balanced equation. And it's a 1-to-1 ratio. 1 mole of CH4 gives me 1 mole of CO2. So I can form 0.189 moles of CO2. Now I'm going to do the same process, but I'm going to do it for oxygen using the parameters that they gave me. For oxygen, which would be 1.25 atmosphere, 35 liters, that's a lot, and then 0.08206 with our units, but I'm going to skip it because I'm trying to save time here, 304 K. And I get 1.75 moles of oxygen. And then I go get my mole ratio. So 1 mole, just kidding, 2 moles of oxygen produce 1 mole of CO2. So that is 0.877 moles of CO2. So clearly this is my answer, and this and then the CH4 is the limiting. So now I have my moles of CO2. So my problem asks for volume, so now I can work a third gas law problem and find the volume. So volume is going to be equal to nRT over P. Now we plug in the moles that we just calculated. So that many moles. Do our R value, 80206. I know, liters per atmosphere. I know it's so tedious. And then the new temperature was 398 Kelvin. And then the pressure at, what was the pressure? 2.5 atmosphere. And then we throw that in the calculator, go back and look, and pretty much need 3 significant figures. So it's going to be 2.47 liters. A lot of work to get to that problem. Okay? And so if you had trouble understanding what I just did there, it wouldn't be a bad idea to back it up and watch again so that you understand why we did 3 gas laws. But just to reiterate, we did gas laws for determining the moles of oxygen and moles of methane, and then did the mole ratio to see how much we could produce to determine limiting. And then we took that amount of CO2 and converted it to volume in a third gas law equation. So that's going to bring us to density of gases, and we already know that the molar volume of a gas is 1 mole is equal to 22.4 liters. So we're showing that with 3 different gases here in this picture, but we're looking at, if you look at the mass of each of those gases, so obviously oxygen is going to be have a higher density than the rest of them. Same number of particles because it's 1 mole, but it's going to be denser because their particles are heavier. So because of that, we can derive from the ideal gas law some formulas that are useful. They are formulas that do not show up on your reference material, so you wouldn't be tested over directly. For instance, when we do the density molar mass equation using density, you can get there another way. But if you know this equation and use it, it's just much faster, easier. So I'm going to recommend that you memorize one of them because you can get to the other one. So if you are interested in knowing how we derive it from the ideal gas law, I can show you. Most students don't care. They just want to use it. And so They sometimes call it the molar mass kitty cat equation because they say when the kitty cat goes to the bathroom, it says meow, meow, and then it puts its dirt over its pee. So sometimes it's called the dirt over pee equation, but that is the density of the gas. And then, of course, your gas law, your temperature, and your pressure. Of course, if we wanted to rearrange that and solve for the density of the gas, we would take and just rearrange that, molar mass times pressure of the gas over RT, and you can get there that way. But honestly, usually we have this one memorized, and we could get to the other one if we needed to. Okay? So that, of course, means that we are going to work a problem. All right, so we have the density of the gas was measured to be 1.95 at those conditions. Calculate the molar mass. So we're going to say molar mass equal to the dirt over P. Now we just plug it in, and we say 1.95 grams per liter, 0.08206 liters atmosphere, okay, and then our temperature, 27 degrees Celsius is 300 Kelvin, and then 1.50 atm. So I want to take a moment and show you how we're able to get to the units that we need. Liters, of course, cancels out, Kelvin cancels out, atmospheres cancels out, and we are left with units of grams per mole, which is the units of molar mass. So when I put that in my calculator, I get 32.0 grams. All right, we're going to end that lesson here, and we'll pick up with gas mixtures and partial pressures in the next video lesson.